I have a bit of a puzzle for you. I've set up two speakers, a very particular distance apart, each playing the same tone at the same volume and being recorded by my camera's microphone. Here's the question: what will happen if I cover one of the speakers? Pause the video now if you need a moment to think about it. This might seem pretty obvious at first. If you block the sound coming from one speaker, the volume should go down, right? Let's take a listen and see what happens. Did you guess correctly? When I cover one of the speakers, the volume actually goes up. And in case you're wondering, the same thing happens if I cover the other speaker instead. So what's going on here? Are my speakers playing at some sort of negative loudness? Is that even a thing? Now, I know this might seem a bit eerie at first. It may feel like it's not allowed by the laws of physics, but rest assured, there's a very sound explanation for this. So just hear me out. Hey everyone, Rohan here from Nexus Audio Visuals. So this phenomenon is equal parts bizarre and fascinating. The principles that cause it are also responsible for an amazing piece of tech that you might regularly use but maybe take for granted. Before we try to demystify this unusual effect, I'd be grateful if you could hit the like button on this video. It makes the YouTube algorithm happy and helps other people discover my channel. With that out of the way, let's get started. First, let's build an understanding of what sound actually is and how it works. There are two main ingredients we need to produce sound. The first is a medium for the sound to travel through. The medium can be any state of matter, a solid, liquid, gas, or plasma. But without a medium, you would have what's known as a vacuum, which is just empty space with no matter. And sound can't travel through a vacuum. For example, there's a near perfect vacuum in outer space, meaning it's mostly empty up there. That's why in space, but thankfully, back here on Earth, we don't have a vacuum. We have air, which consists mainly of gas molecules like oxygen, carbon dioxide, and nitrogen. These molecules, represented here as wiggling circular particles, are free to transfer sound energy by bumping into each other. This transfer of energy from collisions is what allows sound to move across a given distance. The second ingredient we need to produce sound is a sound source. In the case of our demonstration, that would be the two speakers, and more precisely, the vibrating speaker cones. But more generally, a sound source can be anything that oscillates and disturbs the particles in a medium. For instance, we can represent a sound source with this orange T-shaped object moving left and right. As it oscillates, it causes nearby particles to bunch up and spread out in regular intervals. I designed this simulation so that the particles get brighter where the pressure is higher and darker where it's lower. These alternating regions of high and low pressure travel through the medium in waves and eventually reach your ear. Your ear then converts those pressure waves into electrical signals which your brain interprets as sound. But we can actually make that model slightly more accurate. In our 3D world, sound waves move away from their source in a spherical pattern, not a linear one. A convenient analogy for this is the circular ripples created by droplets hitting the surface of water. In this simulation, you can see that the water ripples move away from the source in alternating waves, where the bright bands represent a high water level and the dark bands a low one. If we replace the water drops with a speaker playing a consistent tone, we can see that the pattern looks nearly identical. In the case of the speaker, the bright bands represent high air pressure, while the dark bands represent low air pressure. Now, let's try to look at our sound waves in a more quantitative way. Going back to the analogy of ripples on water, a side-angle perspective of the water's surface would show the water level changing in this curvy, serpentine pattern. It can be useful to think of sound waves in a similar way. This graph of a traveling sound wave depicts air pressure as a function of distance, or how bunched up the air particles are as the sound moves away from the speaker. The high points, or peaks, represent high pressure, while the low points, or valleys, represent low pressure. At the points in between each neighboring peak and valley, the pressure is the same as it is in neutral air with no sound. If you think back to trigonometry class, and I'm so sorry for triggering you, this visual should remind you of a sine wave. In fact, the sound you heard in my demonstration is actually generated by sending a signal shaped like a sine wave to the speakers. The resulting tone is called a pure tone because of its regular, smooth transitions between high and low pressure. Waves can also travel in more erratic patterns like in music or speech. But we'll just consider sine waves for now to keep things simple. Now, let's say we had two identical sine waves traveling on the same path instead of just one. How would these two waves interact, and what effect would it have on the overall volume? Well, that actually depends. If the waves were moving exactly in step with each other, where peaks lined up perfectly with peaks and valleys with valleys, then the effects of the waves would add together and essentially double the overall height of the combined wave. It's important to note here that the loudness of a sound is determined by the difference between the peaks and the valleys of the wave, also known as amplitude. So in this scenario, a microphone or your ear would register the increase in amplitude of the combined wave as an increase in the volume compared to the sound of a single wave alone. This effect, when two waves travel in phase with each other, is known as constructive interference. On the other hand, if the waves were misaligned in just the right way, where each peak from one wave was moving along with a valley from the other, then the waves would cancel out each other's effects. In other words, every high pressure region from one wave would mix with a low pressure region from the other, combining to produce a more constant, neutral pressure. In this scenario, your ear or a microphone would register this decrease in amplitude as a decrease in the volume of the sound compared to a single wave alone. This effect, when two waves travel out of phase with each other and cancel out as a result, is known as destructive interference. With all this in mind, let's take our ripple model of a single speaker and add another one. I think you'll agree that what results is way more interesting than just one speaker alone. Notice that as the sound waves spread out and begin to interact with each other, they produce two prominent types of regions. In the first type, we see alternating black and white bands. This reflects mostly constructive interference, where the two waves amplify each other's effects as they travel nearly or perfectly in phase. If you stood in one of these regions, the tone would seem louder than a single wave alone. But in the other type of region, every peak from one wave clashes with a valley from the other, resulting in neutral air pressure, shown by these gray lines leading away from the speakers. This is an example of destructive interference, where each wave cancels out the effects of the other because they're traveling out of phase. In these regions, the tone would sound muted and maybe even close to silent. And that is the key to solving the mystery I presented at the start of this video. In my demonstration, I positioned my camera very carefully in a region of destructive interference. That's why the sound seems quieter when both speakers are playing, but louder when one of them is blocked. But why does any of this matter in the real world? Well, if you've ever used active noise-canceling headphones, you've benefited from the principle of destructive interference. These headphones work to reduce the loudness of unwanted noises from your environment, like the roar of a plane engine or the hum of an AC. The technology that makes this possible relies on an integrated mic that picks up the incoming noise. The headphones then generate the same exact wave pattern as that noise, but inverted or flipped upside down. As the sound waves travel together, they cancel out and neutralize, which your brain interprets as a lower volume. So, next time you reach for your pair of noise-canceling headphones, take a moment to appreciate the science behind the silence. Between all the steps of the production process, it takes me hours upon hours of work for every minute of footage that you see. It's extremely rewarding and I love doing it, but it's also extremely challenging. So if you made it this far, it would mean a lot to me if you considered subscribing. It's free, helps me continue producing content, and makes it less likely that you'll miss a future upload. And let me just say, I was overwhelmed with the positive response that my last video received. You can click on the info card in the top right-hand corner of your screen to check that out. And feel free to leave a comment down below if you have any thoughts about this topic, or if you have a suggestion for what I should cover next. I truly appreciate each and every one of you for watching. Thanks so much for stopping by, stay healthy, and I'll see you in the next video.